So last time we finished talking about all the planets in the solar system, but it turns out there's a lot of other stuff in our solar system that we need to talk about. So today we'll learn about asteroids, comets, and dwarf planets. And perhaps importantly for life on Earth, we'll talk about what happens when these things impact the planets. So just to review our gas giants, what material is responsible for the magnetic fields of Uranus and Neptune? So solid iron core is for the rocky planets. Jupiter and Saturn have metallic hydrogen, and then Uranus and Neptune have a liquid water methane layer that gives them a magnetic field that kind of wobbles all over the place. Okay, so we'll start from the objects closest to the sun and work our way outwards. So the first group of objects that are not a planet or a moon are the asteroids. So these are rocky inner solar system material. And if you were to take a picture of some region in space, this is what an asteroid might look like in your picture. So all of the stars are not moving. And so if you see something that makes a streak across your image, then you have something that's moving pretty quickly. So that could be an asteroid in the asteroid belt. More commonly, it'll be a satellite orbiting the Earth. So you can, just by taking pictures of space, you might be able to find something interesting. And so that's what it looks like in our picture from the Earth, and this is what it looks like send probes out and explore asteroids themselves. They're just kind of lumps of rock floating out in space. Comets are mainly in the outer parts of the solar system, but every once in a while their orbits will come close to the sun, and they get these very pretty appearances in the night sky. So we'll come back to talk about the anatomy of a comet in a little bit. And then dwarf planets are things that are going to be big enough that they have a spherical shape, but they're not big enough to, for example, be the biggest thing in their orbit. The discovery of Eris, which is another dwarf planet out beyond Pluto's orbit, is kind of what kicked off the discussion as to what a planet is. Because if Pluto is a planet, then you'll have to include Eris as a planet as well. So the astronomical community decided instead of making them both planets, they would make neither of them planets, and they would have a new designation called a dwarf planet. So some of these objects will impact the Earth, or at least enter Earth's atmosphere. And so a meteor is a flash of light produced by some small object that enters the Earth's atmosphere. And then if that object survives its trip through the atmosphere, it doesn't get burned up, and it hits the ground, then it's called a meteorite. So that's the two definitions. Meteor is when it's still in the sky, and it's actually just the light that's being produced, and meteorite is the physical object if it actually makes it to the ground. Most of the meteorites that we find on Earth are pieces of asteroids that have been kicked out of the asteroid belt and have landed on the Earth. So we'll talk about what asteroids are like, and using some of the samples that we have collected from the ones that have hit the Earth, we can talk about their composition. And we have started to send probes to asteroids to collect samples as well. So these are kind of the leftovers of planetary formation. So at the very beginning of the solar system, this is kind of what the whole solar system, or at least the inner solar system, would have looked like. These small bits of material, and over time, the planets were built up by a lot of these material colliding and growing a bigger and bigger planet. But we'll talk about what prevented the things in the asteroid belt from becoming a planet themselves. We have catalogs of what we've detected in the asteroid belt, 150,000 objects that are that we know about that are over a kilometer in diameter, but we probably think there's over 1 million. It's just they're very small and they don't produce their own visible wavelength light, so it's very hard to detect them. And there's even more asteroids that are smaller than 1 kilometer. We'll talk about the sizes of asteroids and what kind of damage they can do later. But bigger asteroids are going to do more damage than the smaller ones. If you were to take all of the mass of all the asteroids in the asteroid belt and make a planet out of them, it would be still the smallest planet in the solar system. So it would be much smaller than Mercury. There is the largest asteroid in the asteroid belt is actually classified as a dwarf planet. It's big enough that it's spherically shaped, but because there's a bunch of other stuff in its orbit, all the other asteroids, it's not considered to be a planet, it's a dwarf planet. So these are real pictures of asteroids that we've sent probes to, and for the most part, they're not big enough to be spherically shaped, so they're all kinds of irregular shapes, and they have lots of cratering on their surface because they've been hit with other objects and there's no geologic activity to smooth out those craters. This is Ceres, which was this is the largest asteroid in the asteroid belt. You can see it's spherically shaped, and it has evidence of craters, but it also has evidence of smooth features, so there might have been some geologic activity at some point for Ceres. And it's not all just one type of material. You can see there's bright spots that might be some salts or some other minerals on the surface. And so it does have things like mountains, and so it's not just a totally uninteresting thing out in the asteroid belt. It's very similar to what you would expect a planet to look like. There are asteroids that have moons orbiting them, and they don't have to be the nice spherical asteroids. So this is the asteroid Ida and its small moon Dactyl. And so you can see Ida is not spherically shaped, but had enough mass to capture this little tiny asteroid that's now orbiting it. Like I said, we started to send probes to these asteroids, and so the Japanese were the first to touch down on an asteroid and collect samples and bring them back to Earth, and the US has followed suit with NASA's OSIRIS-REx mission, also landing on an asteroid and collecting samples. So here's a video of the Japanese landing. Starts off kind of slow, and then it'll pick up. So this is them. Basically, they just touch the surface of the planet, kick up a bunch of material, and then collect some of that material to bring back to the Earth. So they're briefly landing on the asteroid, just enough to kick up a bunch of debris, and then collect some of that debris to bring back to the Earth. So one of the ways that we can study asteroids is by going there. The other way is by looking at the meteorites that we can collect on the Earth. So for the most part, these are going to be asteroids that fall towards the Earth, but there's going to be different types of meteorites that will be coming from different objects. So the primitive meteorites are the ones that are going to be coming from asteroids. So these are rocks that don't show any evidence of geologic activity. So whatever rocks you had at the creation of the solar system, those were in the asteroid belt, they hit the Earth, and then we can study basically the building blocks of the solar system. But then there are these processed meteorites. So these are meteorites that we collect, but they show signs of geologic activity. So they had to have come from some object that, say, experienced volcanism or differentiation. And for the most part, that's not going to be from an asteroid. So it turns out these processed meteorites are actually chunks of different bodies in the solar system. So we have collected rocks from the moon and Mars and other solar system bodies. So if you have a big enough impact on, say, the moon, some of that material will get kicked out into space, and some of that material might land on the Earth. So this is a kind of a cheap way to collect material from a different planet, but you're only ever going to get probably the surface material from that planet, and it's going to take a very long time to build up any kind of meaningful sample, because the meteorites might not survive the trip through the atmosphere, or it's also not easy to find a meteorite once it hits the ground, especially if it's very small. So where do these asteroids come from? They mainly live in the asteroid belt, which is this big white cluster between the orbits of Mars and Jupiter. There are Trojan asteroids. They basically precede and follow the orbit of Jupiter, and that's a consequence of orbital mechanics. These are called Lagrange points, and they're stable positions that have to deal with the orbit of Jupiter and the gravitational impact of the sun. And then there are some other asteroids that have been kicked out of the asteroid belt and are in the inner solar system that cross the orbits of some of those planets. So we call the ones that cross Earth's orbit to be near-Earth asteroids. And those are the ones that you have to watch out for like doomsday type scenarios. So we haven't necessarily talked about the formation of the asteroid belt, but which of these do you think is the most plausible explanation? Yeah, so the asteroid belt is just where what material you had at the beginning of the solar system, that material that could only survive in a place like the asteroid belt. If it was in the orbital path of any of the planets, it would have impacted one of those planets a long time ago. And there was no planet that formed in between the orbits of Mars and Jupiter, and we'll talk about that in a second. If you look at the location of the objects in the asteroid belt, you'll find these gaps, and they have to do with orbital resonances with the planet Jupiter. So Jupiter's orbital period is on the right of the graph. You can see there is a population of asteroids here. So those are the Trojan asteroids that are before and after, that precede and follow Jupiter's orbit. And then at these very precise fractions, you also have gaps. And so these are orbital resonances. So the asteroid will orbit 4 times and Jupiter will orbit once. That means that at some point the orbit of that asteroid and Jupiter will line up such that it's feeling a strong gravitational pull from Jupiter. This one, an asteroid would orbit 3 times for every 1 time that Jupiter orbits, and then again you get a stronger gravitational pull from Jupiter, and that will knock you out of your orbit. So Jupiter has basically cleared these gaps in the asteroid belt just by having a really big mass that will pull these asteroids out of orbit. So like I said, the asteroid belt is kind of just this is what the solar system would have looked like very early on, and there was not a planet that formed in this region, and so there wasn't something to collect all of this extra material, basically. And so the influence of Jupiter, and to a lesser extent Mars's gravity, prevented a planet from forming here, and so the asteroids are really just the leftover building blocks of the early solar system. So asteroids, the rocky leftovers of planetary formation. Most meteorites that we collect on Earth are from asteroids, but we do get some from, say, other planets or our moon. Why is there an asteroid belt? You get gravitational influences from Jupiter and Mars that prevented any planet from forming in that region of space. And so the asteroid belt is just the leftover material. Any questions about asteroids? So then we'll talk about comets. So we'll talk about where they come from and why, unlike, say, an asteroid, they will have this tail that forms. So these are going to be kind of the leftover material of solar system formation, but these objects formed beyond the frost line, and so instead of being rocky, they're going to be more icy. They will have what we call a nucleus, which is the center of the comet, and that'll be like a dirty snowball. So it'll be ice, but also little bits of rock. Usually they will not have a tail, and only when they get closer to the sun will they start to grow a tail. But most comets, and for the majority of the comet's life cycle, it will be outside of it'll be in the outer part of the solar system, not close to the sun. Okay, so here's the anatomy of a comet. You have what you would think of as the actual object in the center, the dirty ice ball. But then you'll have a region of gas around the comet called the coma. And so this is material that's being outgassed when it gets close enough to the sun that it starts to evaporate some of the ices that make up the nucleus. And then you'll actually get two different types of tails coming off of the comet. So the comet is moving in one direction, and the light from the sun is coming from potentially a different direction. And so you get a plasma tail that is basically pointed exactly away from the sun. And then you'll get a dust tail that's a combination of the opposite of the two vectors pointing towards the sun and the comet's motion. So you have some of the solar wind pointing this way, and then you have the comet's motion pointing this way. And when you add them together, you get a dust tail pointed not necessarily in the same direction as the plasma tail, but slightly off from that. So here's kind of the cycle of a comet. It'll start very far away from the sun, and typically comets that come close to the sun will have this kind of highly elliptical orbit. You'll start far from the sun. As you get closer towards the sun, your nucleus will start to warm up. Then you'll start outgassing some material as ice starts to evaporate, so you'll develop a coma. Then you'll develop your tails when you're really close to the sun, and depending on where you are in your orbit, your plasma and dust tails might not be in line with each other. And then as you start receding from the sun, you'll start to lose your tail, then you'll start to lose your coma, and then you'll be back out in the far reaches of the solar system to do it all again in maybe hundreds of years. And that's assuming you have enough material left over to keep doing this, because eventually you'll outgas too much material and you won't be able to grow your tail anymore. So in addition to sending probes to asteroids, we've also sent the Rosetta mission to a comet. And so this was orbiting the comet as it approached the sun, so we could see the coma start to develop, and for example, a jet of evaporated material shoot out from the surface of the comet. And so this is actual footage from the surface of a comet. And it's just being looped over and over again. But I just think it's interesting to see if you did send a person to a comet, what might it look like? So you've got a bunch of dust swirling around. You can see some background stars, because of course there's not going to be any atmosphere around this comet, so you could see stars very easily. But it's not just like a smooth object. You can see there's just rocks scattered around the surface. And so I just think it's really neat to see what it might look like if you were to land on a comet. So the other phenomena that you might be familiar with are meteor showers. So for meteor showers, this is from our point of view, it looks like we have a bunch of stuff raining down from the sky, but really these objects are just orbiting the sun, and we're basically plowing through their orbits. And so it's really the Earth that's the thing moving really fast and causing these objects to come down towards the Earth. So the analogy is the same as when you're driving through snow. The snow, if you were just standing still, the snow would kind of be falling slowly. But then if you start driving quickly through the snow, it kind of looks like your favorite sci-fi show or movie where they engage warp drive and everything looks like it's stretched out and moving by really quickly. So where are these comets coming from? For the most part, they are going to be beyond the orbit of Neptune, and so they can either come from the Kuiper belt, which is the icy belt that's beyond the orbit of Neptune that includes things like Pluto, or it could come from the Oort cloud, which is this spherical shell of material that's even farther out from the sun. So Kuiper belt is 30 to 50 times farther away from the sun than the Earth is. There's tens of thousands of comets there. But then in the Oort cloud, which is 50,000 times farther away from the Earth, from the sun than the Earth is, you've got trillions of comets with all kinds of random orbits and different kinds of eccentricities. So again, where did this material come from? It's leftover material from solar system formation. For the most part, the Kuiper belt is all aligned or fairly closely aligned to the plane where the planets orbit the sun, and they all orbit more or less in the same direction. And then the Oort cloud, these might be things that were kicked out of the Kuiper belt or the outer and inner solar system by interactions with some of the planets, and so these are spherically distributed and they have lots of random orbits. We've also seen objects from other star systems. So on the left is Oumuamua, and on the right is 3I Atlas. And by studying the motion of these objects, you can basically calculate backwards where that object must have come from, and we can tell that it's not a solar system object. So the reason the pictures look like this, so we said if you wanted to take a picture of an asteroid, you could just take a picture of the sky and you'd see a streak. This is basically the inverse of that. If you want to study the moving object, then you don't want to try to study a streak. You want to focus on that particular object and keep it in the center of frame. But since it's moving, it'll look like everything else is moving with respect to the thing that you're trying to keep in the center. So these are all background stars that, let's say this was taken over 12 exposures, then you add up all of those exposures so you can get basically a brighter image of this very faint solar system object. So 3I Atlas is in the solar system right now and is going to be at perihelion, so its closest approach to the sun, at the end of this month. So there's a lot of interesting science being done with this visitor from another star. But no, it's not aliens. So we'll talk about aliens next week. So why do comets grow tails? For the most part, they don't have a tail, and it's only when the sun heats up the nucleus and it's exposed to enough solar wind that you will get a tail. And comets are in the Kuiper belt and in the Oort cloud are the leftover material from solar system formation. Okay, so we'll talk about some specific objects in the Kuiper belt, mainly Pluto. And this is a real image that we've taken of Pluto. And it turns out Pluto is a bit more interesting than we thought it would be. So firstly, it's in basically a binary system. Its largest moon, Charon, is almost the same mass as Pluto, and so it's not one orbiting the other really, they're both kind of orbiting each other. It's very cold. When it gets close to the sun, it will have a thin nitrogen atmosphere, and then as it gets farther away from the sun, that atmosphere will basically freeze out and fall back towards the planet. And all of these pictures and data that we've gotten of Pluto are from the New Horizons mission that only recently made it to Pluto. And so this mission was launched before, when Pluto was still a planet, and it didn't get there until after Pluto was already demoted to a minor planet. So we talked last time about how Pluto's orbit is tilted with respect to Neptune's orbit, and so they would never hit each other. Pluto won't ever get tugged by Neptune's orbit because of an orbital resonance. So for every 3 times Neptune orbits, Pluto will orbit twice. And so at the time when Pluto crosses Neptune's orbit, they're never actually in the same part of their orbit to interact with each other anyways. So when Pluto was first discovered in 1930, this is what we could see of it. Then even with the Hubble Space Telescope, we could only get a very fuzzy picture, and it wasn't until we sent a probe directly to Pluto that we could get this nice, pretty picture of what Pluto actually looks like. And like I said, it's a bit more interesting than scientists originally thought. So there are mountains that are as tall as the Rocky Mountains on Earth. And again, Pluto is much smaller than the Earth is. So having a mountain that's that big is actually, you can think of it as being even bigger because Pluto is much smaller than the Earth is. And again, this is an icy world, so these mountains are not made out of rocks, they're made out of most likely water ice. And there's some evidence of some kind of liquid flowing on the surface, or maybe not liquid, but some nitrogen ice flowing on the surface. And as you can see, there's some evidence of cratering, but there's also very smooth regions on the planet. So that indicates some kind of geologic activity. So this is Charon, which was with Pluto's moon. And again, you can see evidence for geologic activity on Charon as well. Arrokoth is the lumpy orange object on the right, and that's another Kuiper belt object. So after New Horizons went by Pluto and Charon, it imaged Arrokoth as well. But you can see this is very different looking than Pluto or Charon. So the stuff that's out in the Kuiper belt is not necessarily a uniform distribution of icy things like Charon and Pluto. So we don't really know much about the Kuiper belt objects. They're very far away, so it makes it very hard for us to see them. And we really only sent our first probe there with New Horizons, and it went to Jupiter, or not Jupiter, it went to Pluto and Charon, and then a couple of the other small Kuiper Belt objects, but there's thousands of objects out there, just very far away and very hard to study. So Pluto has a very elliptical orbit compared to the other planets, and it has a tilted orbit. It does have a system of moons. There's evidence of geologic activity on the surface of Pluto, and we don't have a lot of data on Kuiper Belt objects, so we kind of have to base any inferences we can off of the little data that we have from Pluto. Okay, so that's kind of a summary of the objects in the solar system that are not big enough to be planets. And now we're going to talk about what happens when those objects hit a planet. So we'll talk about, for example, the extinction event that killed the dinosaurs, and then we'll talk about what we can do as humans to try to save ourselves from future impacts. So, did an impact kill the dinosaurs? That's the leading scientific theory. And when we talked about Jupiter, we talked about the impact of comet Shoemaker-Levy 9, and so there is still large impacting events happening in our solar system today. And so we know these kind of impacts happened a lot in the past, but we have evidence that they're currently happening, and so that should give humans living in the solar system a little bit of cause for concern. If you look at the fossil records on Earth, there are several periods where the biodiversity drops precipitously, and we call these mass extinction events. And the most recent mass extinction event was 65 million years ago, and that ended the reign of the dinosaurs. So that was the dominant organism at least on the surface of the Earth. And so something happened that caused this mass extinction event. We have evidence that there was a very large impact that also occurred 65 million years ago. So iridium is a material that's very rare to find on the surface of the Earth, but these two geologists found a thin layer of iridium basically all around the Earth that coincided with the time period of 65 million years ago. So iridium is rare to find on the Earth, but it's fairly common to find it in asteroids. And so you have this layer of iridium, no dinosaur fossils above it, all the dinosaur fossils below it, and so that leads to the theory that some large impact occurred, deposited all this iridium on the surface, and killed the dinosaurs. So then you have to find an impact crater that's big enough that could explain something that could deposit iridium all over the surface of the Earth. And so they found evidence of a pretty large impact kind of in the Gulf of Mexico and on the Yucatan Peninsula. So if you look at the outer part of the crater, remember we said there was a scaling factor. I think it was 10 times the size of the impactor for the size of the crater it makes. And so if you look at this impact crater, it would tell you that the impactor had a size of about 10 kilometers. So 6 miles, so about the size of a city, but a city that's moving very fast and plowing into the Earth. So something this big hitting the Earth would have put a bunch of debris into Earth's atmosphere, including that iridium, it would have been enough stuff in the atmosphere to block sunlight, and so your whole food chain is going to break down, basically. If you don't have enough sunlight, you're not going to have a lot of plant life. Then you're not going to have things that eat the plants, and you're not going to have things that eat the things that eat the plants. So you could think about this as climate change, because the asteroid kicked up enough stuff into the atmosphere to cause the climate to change, and life can adapt, but not quickly enough to an event that happens very quickly. And so obviously some life survived, so mammals were able to adapt and survive, and we are the descendants of those mammals. So asteroids and comets have hit the Earth in the past, and so a major impact is not really a question of if, but when. The major impacts are rare, so an extinction level event, we haven't had one for 65 million years, so we know it's at least on the order of millions of years. But smaller events that can cause major damage to, say, a city, those happen on the scale of tens to hundreds of years. So here are some recent impacts that have occurred. A couple in Russia. So this one was captured by someone's dash cam. And so this particular asteroid exploding had an equivalent of a 500 kiloton nuclear bomb. Tunguska in Siberia. This was a 40-meter object that exploded in the atmosphere and caused damage for hundreds of kilometers to the surrounding area. So you can see this happened in Siberia, so it's not like there were people around to see it, but you can see the shockwave of the explosion knocking down trees for hundreds of kilometers. These particular events, the asteroid actually blew up in the atmosphere before it made it to the ground, but then you have something like meteor crater. So this was a 50-meter object that actually made it all the way to the surface, and this happened 50,000 years ago. So there would have been humans on Earth at that time. There weren't humans in North America, so they wouldn't have been right here, but they might have very well seen a very bright object in the sky. And so these are things that, as a civilization, we need to worry about. The frequency of impact, so very small things that don't make it out of the atmosphere or explode in the atmosphere happen pretty much every day. Then on the scale of something leaving a crater, you're getting into the hundreds of years or thousands of years. Something that's actually going to cause damage to, say, a city, maybe you're in the millions of years. And then something like significant climate change or mass extinction event, you're looking at hundreds of millions of years. But it's been 65 million years since the dinosaurs went extinct, so perhaps we are due for something. I'll give you all some time to think amongst yourselves about any methods you can come up with that might deflect an asteroid from hitting the Earth and save civilization. I'll just talk about some of the ideas that scientists have come up with to deflect asteroids. So you can go the Hollywood route and send miners to the asteroid and detonate a nuclear bomb inside of it. You can place mirrors on the asteroid and try to use lasers to push the asteroid off its path. Or you can just directly use the lasers to heat up the material in the asteroid, cause it to outgas some material and change its orbital trajectory. You can attach rockets to it to try to change its trajectory. You can smash into it with a spaceship. You can attach solar sails to it to change its trajectory. Or if you paint it in different colors, you can cause some of it to heat up and maybe outgas material to change its orbital trajectory. So we've actually tried one of these methods. So we've sent a spaceship to an asteroid to try to hit it to see if we can actually alter its orbital path. So this is NASA's DART mission. And so they picked an asteroid, the small one that's orbiting a larger asteroid, and they hit it with this probe that they sent, and then studied how that impact changed its orbit after the collision. So, have we identified any asteroid that's going to kill us? No, we haven't seen it yet. If we do detect such an asteroid, then we have a better chance of deflecting it if we have a lot of time to influence its orbit. And just blowing it up is not really a good idea. You want to do whatever you do in a controlled manner. A bunch of small asteroids hitting the Earth could cause just as much damage as one big asteroid. For comets, we have a bit less warning because it's going to be coming from farther out in the solar system, and so we might not see it until it gets closer to us. And I'll leave you with some thoughts on asteroids and kind of life on Earth. So Jupiter is capable of redirecting outer solar system bodies from hitting the Earth, or it might nudge their orbits in such a way that it actually makes them on an impact course with the Earth. So Jupiter, and to a lesser extent Mars's gravity, has kind of prevented the asteroid belt from forming one solid object, and so there is this reservoir of asteroids that could in the future hit the Earth. But on the flip side, humans would not exist if there wasn't this big asteroid impact that wiped out the dinosaurs. So impacts from asteroids or comets could extinguish life, but you might argue at least the life that we have on Earth wouldn't be possible without these kind of impacts. So next time we'll talk about exoplanets, and after that we'll talk about life in the universe. And so keep in the back of your mind what having things like asteroids or comet impacting a planet has on its potential for life.